Hello and welcome to the channel. The periodic table is often overlooked by most students, but it reveals a host of information about basic chemistry that can be used to aid and embed understanding, and it's freely available in an exam so you can recall information easily. In this video we are going to discuss some of this information, starting with general observations, then move on to valency and bonding, trends in physical and chemical properties, and lastly understand electron configurations in more detail. Let's start by looking at this more comprehensive version of the table. The columns or groups are numbered from left to right from 1 to 13. However, in abbreviated versions and for GCSE chemistry, the portion in the middle containing the transition elements, lanthanides and actinides, are usually ignored, and the groups go from 1 to 7, with the last one being either 8 or 0. The rows are called periods and are numbered downwards. We will discuss the significance of groups and periods later. Although hydrogen is seemingly in group 1, chemically it's not, and in other versions it usually just sits on its own. There are also two groups which are usually shown as two additional rows below the main body of the periodic table. These are the lanthanides and actinides. The lanthanides are rare earth metals and have important industrial uses. The actinides are radioactive metals, only a handful of which are naturally occurring on Earth. Let's now look at what the numbers mean, using magnesium as an example. The number 12 is the atomic number, or the number of positively charged protons, and this is also equal to the number of negatively charged electrons, as atoms are electrically neutral. The atomic number is unique to a given element, and it is this that defines an element. The number 24.3 is the relative atomic mass. If the atomic mass was exactly 24, then that means there are 24 nucleons in total. In other words, 12 neutrons in addition to the 12 protons. The 24.3 is a weighted average of the relative masses of the various isotopes that are found in a sample of magnesium. Remember that isotopes are versions of a given element which have different number of neutrons. The relative atomic mass is relative to a reference. The reference used is 1/12 of the mass of a carbon-12 atom, i.e. a carbon atom with 12 nucleons. This is approximately equal to one hydrogen atom. Let's now move on to the physical form of the elements. The vast majority are metals, and these occupy the table up to the yellow zigzag section on the right from boron to polonium, which contains semi-metals. These exhibit properties of both metals and non-metals. As most people know, metals generally have high melting points, good thermal and electrical conductivity, and are hard but malleable and ductile. These properties are the result of the strong metallic bonding, where the outer shell electrons are delocalized. Metals form positive ions by losing electrons. The groups mostly studied in school chemistry are the group 1 alkali metals, the group 2 alkaline metals, and some of the transition and basic metals. As we move left to right across the periodic table, the elements become less metallic, in that they tend to want to gain or share outer shell electrons rather than lose them. The blue section on the right contains the non-metals, most of which have low melting and boiling points. When non-metals are in a solid state, they are usually brittle. Apart from graphite, which is a form of carbon, they are poor conductors of heat and electricity. We will now move on to what we can learn about valency and bonding. The term valency refers to the number of outer shell electrons involved in these bonds, which can either be ionic or covalent. Here we have a simplified periodic table. This shows the groups from 1 to 7 and the noble gases as group 0, although it was previously known as group 8. In the last section of this video, we will be discussing electron configuration in more detail as studied at advanced level. However, for the more basic level, it is only necessary to know that period 2 has 2 principal shells of electrons, period 3 has 3, and so on. In addition, for the groups shown, the maximum allowable number of electrons in the outer shell is 8. When electrons want to form compounds through bonding, they generally wish to do so by forming a stable full outer shell, either by losing, gaining, or sharing electrons. Now the number of outer shell electrons is given by the group numbers shown. Thus the alkali metals in group 1 have 1 outer shell electron, which they want to lose in order to gain a stable full shell. The group 2 elements wish to lose 2, and so on, up to group 3. These elements form ionic bonds, and the valency number corresponds to the positive charge on the ion, resulting from the loss of electrons. When we get to group 4, the elements wish to share their 4 outer shell electrons with 4 other electrons from another atom to form a covalent bond, which allows a stable outer shell of 8. A good example of this is carbon, which has a valency of 4, which enables it to form countless compounds with many other elements, and is the key to organic chemistry and the existence of life. In group 5, the valency drops down to 3 because these elements need to share 3 electrons for a full shell. The valency in group 6 is 2, and here the elements, most notably oxygen, form both ionic and covalent bonds. In the much studied group 7, the halogens, the valency is 1, as the elements form -1 ions, as they capture an electron to form a full shell of 8 electrons. The noble gases in group 0 have full outer shells, and so have a 0 valency. They do not form bonds with anything, even with themselves, and they exist as single atoms. The valencies allow you to predict the chemical formulae of simple compounds. Here 4 examples of ionic compounds are shown, and the formulae are derived simply from balancing the charges. In the case of compounds formed by covalent bonds, the valencies are equal. For example, ammonia has the formula NH3, and the valency of 3 for nitrogen is equal to 3 times the one from the hydrogen atom. Let's now proceed to learn what kind of trends in physical and chemical properties can be revealed by the periodic table. In groups 1 and 2, the reactivity increases as we go down the group. This is because as the atomic size increases, outer shell electrons are, on balance, more loosely attracted to the positive nucleus, which allows easier electron loss and hence formation of ionic bonds and compounds. It should be noted that the strength of attraction of outer shell electrons depends on factors such as the number of protons, atomic radius, and the shielding from inner shell electrons. If we move to group 7, the halogens, the opposite trend is evident, as the reactivity increases up the group, with fluorine being not only the most reactive element in the group, but probably in the entire periodic table. The reason for this trend is the opposite of that for groups 1 and 2. In group 7, the elements attract an electron to form a negative ion. As the atomic size reduces up the group, on balance there is a greater attraction from the nucleus, which allows electrons to be gained more easily. Let's now look at physical property trends. Take groups 7 and 0. Here the boiling points increase down the group, because as atomic size increases, intermolecular forces between atoms increase, meaning more energy is required to break them. In group 7, melting points follow the same trend. For example, at room temperature, fluorine and chlorine are gases, whilst bromine is a liquid and iodine a solid. Lastly, let's look at the trend across periods 2 and 3. As we move from left to right up to group 4, the melting points and boiling points increase. For metals, this is because more electrons are lost to form ions, which both decreases the ionic radius and increases the number of delocalized electrons. This leads to metallic bonding strengthening. In group 4, elements with giant covalent structures such as carbon and silicon have very strong bonding and high melting points and boiling points. When we get to group 5 onwards, the elements are non-metallic and more subtle trends apply. Let's now lastly look at electron configuration in more detail. This is applicable to A-level standard in the UK. As mentioned earlier, the number of principal shells, also known as principal quantum numbers, is equal to the period number. So period 2 has 2 principal shells, and so on. However, each principal shell has subshells consisting of one or more of s, p, d and f orbitals, which increase in energy level in that order. We are not going to discuss f orbitals in this video. Electrons fill lower energy shells and orbitals first, those closest to the nucleus, and then the higher energy ones. The maximum number of electrons allowed in each type of subshell is shown in the box. S orbitals start filling from principal shell 1, P from 2 and D from 3. So let's go through the simplified periodic table starting with lithium, which has 3 electrons. Lithium is in period 2 and has 2 principal shells. Shell 1 has 2 s orbitals and is full. Thus from lithium, the shell 2 s orbitals start to fill. Going across the period, beryllium has 2 full outer s orbitals, and from boron onwards, the p orbitals start to fill up. When neon is reached, the outer p orbitals are full with 6 electrons. For period 3, a third principal shell is added, and the same pattern is repeated. Again, sodium has 1 outer s orbital, while argon at the other end of the period has 6 outer p orbitals. Thus, group 1 and 2 are referred to as the s-block elements, because they have either 1 or 2 outer s orbital electrons. Similarly, the block to the right is referred to as the p block, because they have 1 or more outer p orbital electrons. Now when we reach period 4, things get a bit more complicated. Firstly, you would expect the 3d orbitals to start to fill at potassium, but it turns out that the s orbitals in the 4th principal shell exhibit a lower energy than the 3d orbitals, and so they fill up first. The reasons for this are outside the scope of this video, and you do not need to know them for A-level. Thus potassium has 1/4 shell s electron and calcium has 2. The configurations from period 4 onwards are usually abbreviated to argon, which is the end of period 3, plus the additional new electrons. Scandium is the point at which the 3d orbitals start to fill progressively, all the way up to zinc, when they have the maximum allowable 10 electrons. There are a couple of anomalies on the way in the filling process, but we won't discuss those here. When we get to gallium, the p orbitals start to fill, all the way to krypton when they are full. The pattern is repeated for periods 5 and 6. Thus the block of elements in the middle of the periodic table are known as the d block, because they have 1 to 10 outer d orbital electrons. This block is also known as the transition elements or metals, and have very important industrial uses. Most of them form a variety of positive ions by losing the s orbital electrons first, followed by the d electrons. We could go on to discuss more, but that concludes this video. Please subscribe to the channel to see more like this. See you in the next one.